Hello, everybody. This is Dr. Weber. This is the first of many lectures that you are going to be having during the course of this semester. And the purpose of these mini lectures is to present to you information in a similar way that we would have done in class together. So what I like to do is to lecture for a little bit, take a break, do an activity to practice learning some of those skills that I talked about and those topics I talked about during the lecture. So I call this active learning. Active learning is when you learn something and then you immediately get to experience it and practice it and work through it and ask questions. So you're going to be watching some of these lectures that I've put together, and then you're going to be working through a set of a few simple questions in Canvas that you have to submit every Tuesday and Thursday in order to be sure that I know that you're working through the material as you should be, similar to how we would have been doing it in class together. So this week, we are covering material talking about motion, particularly motion in one dimensions. And before we get to that though, I want to talk about something called Bloom's taxonomy. Bloom's taxonomy is a set of hierarchical models used to classify educational learning objectives. And so here is our Bloom's taxonomy for our physics class this semester. You see that we start here with lower order thinking skills, and then we want to progress toward the end of the semester to get you familiar with these higher order thinking skills that we will accomplish, hopefully, in physics this semester. An example of one of these lower order thinking skills for physics would be remembering. Just remembering facts, units, knowing laws and equations. You don't have to memorize ever any equation that I'm going to ask you to use during the course of the semester. You're actually going to be, I'm going to be giving you an equation sheet, which you can use throughout this whole semester, and you start with those equations and you can work from there. I'm not interested in can you memorize a long string of equations. What I am trying to assess though is how you have grasped the problem-solving techniques that we need to use in physics and how you're solving that physics puzzle in order to get toward a reasonable solution. So if we start here with remembering, for us in physics, essentially that means I want you to remember the different kinds of units that go along with different quantities that we're wanting to solve for this semester, to memorize a few pieces of information. For instance, to know in your head that the speed of light is 3 × 10⁸ meters per second, to know that there's 100 grams and a kilogram, 100 centimeters and a meter. Things like that are simple things that I would hope that you would pick up through and remember during the course of the semester. I want you to be familiar with using equations, but I'm not going to ask you to memorize those equations. As we progress up on this hierarchy scale, the next piece is understanding. I would like for you to be able to explain to me a physical law or equation. If I gave you an equation and sat it in front of you, let's say I gave you an equation called Newton's second law, which tells us that the force of an object is equal to its mass times acceleration. If I gave you that equation, I would hope that you would be able to explain to me what that equation means and why it's useful. That's part of understanding. And applying, we're going to apply the physical laws that we're going to learn this semester and equations that go along with them to solve simple problems. And some of them will be simple, but they're definitely going to get a lot more complex. So we're going to learn information. I'm going to show you an equation, and you're going to apply that equation to solve a problem. And then we're going to analyze. And so we're going to take it apart, look at its constituent components, figure out what we can do to solve the problem, and then put it back together. So here we're going to read a lot of story problems, essentially, about physics applied to our universe. We're going to have to dissect it, understand what physical laws apply to that situation, and then put it back together again. A lot of physics is problem solving. And it's like putting together a puzzle. And that's why I really like physics. When you read a story problem, it's about solving that puzzle. And that's what we're going to be this semester. We're going to be puzzle solvers too. And then these top two here, we will encounter them maybe more so in lab than we will in our lecture course. But part of the higher end of our hierarchy on Bloom's taxonomy is evaluating physics problems. We will contemplate and compare different methodologies for solving the very same problem, and we're going to examine lab experiments and quantify possible sources of error. So this last one will occur mostly, of course, in our lab course. This first one, during the course of the semester, I might, especially in discussions, be doing something like this, where I might give you a problem that was solved in 2 different ways by 2 students and ask you, previous students, and ask you to compare and contrast how one solves those problems and what the students might have done wrong, what they did right, and maybe see how there are actually many ways to a similar solution in our physical world. And then we can synthesize physical laws by creating and solving new problems that you haven't seen before. We can derive new relationships among physical quantities using existing physical laws. So this last one here is maybe the most important one as a physicist, like as someone with the physics PhD that we do in our research, is to perform experiments and derive new relationships that we haven't seen before that can explain our universe. We can synthesize physical laws that you haven't seen before, new problems that you haven't seen before, but I've given you all the tools in order to solve that problem. So maybe you'll encounter some things like that this semester. I also might be asking you at some point in the semester to create your own problems. Come up with your own problem based around a particular topic, solve it, and come up with a reasonable estimation for that answer. Maybe that's something that we'll come to toward the end of the semester as well. So with that in mind, let's jump into our first mini lecture, which is going to be about displacement. Every week, I will be giving you the slides that I'm going to go through here as a PDF, so you can look through them and use them as your own notes and follow through what I'm presenting to you right here. During week 2, we are focusing on chapter 2, one-dimensional motion, motion along one axis. The first thing that we talk about when we talk about motion in one dimension is displacement. Displacement is the measure of how far you are in a given coordinate system from a starting point. So imagine that you're looking at a graph and you have a coordinate system. We center ourselves at the origin, and we can move along the x direction, or we can move vertically along the y direction. So in this section of the book, we're talking about motion only in either the x or only in the y. We're not going to combine the two until we get to next week. So displacement is this measure of how you are from your starting point in any coordinate system, here along the x or y direction. But your position is where an object is at any particular time. So your position is just essentially your location, but your displacement is a distance or a measure of how far you are from your starting point. Okay. A displacement is a change in position. So when we're talking about changes in physics, astronomy, math, we're going to represent those by a capital Greek letter delta, which looks like that little triangle. Okay, so we can write an equation for displacement. Here's our first equation. Displacement delta x, the change in our x position, our position along the x-axis, which is the horizontal axis, is equal to our final position minus our initial position. So here this little sub f means final, this little sub 0 means your initial position. Anytime you see a little sub 0, that means that's your starting point, your initial condition. Okay. So the distance that we travel when we're on a particular journey is the total length of the path traveled between 2 positions. Okay, and if you arrive back at your starting point, then the distance that you travel will be non-zero, but your displacement will be 0. So here's a great example of what I mean by that. So imagine that you're on a track. You're on a circular running track, okay? You start at the starting point, you go all the way around the track, and then you end at the same point where you started, okay? So your total distance traveled would be the total length of your path then. So that would be essentially the circumference of that circle, of that circular path you were just walking around. That would be your total distance traveled. But your displacement, remember, is your final position minus your initial position. So if you end up back at the same point where you started, x final minus x initial will be 0. So your displacement will have been 0 because you ended up where you started. But your total distance traveled would then still be non-zero. It would be that total length around your path. So here's an example of displacement. Your lovely physics professor is walking from left to right along the chalkboard, okay? And so the starting position was 1.5 meters from the 0 point on the x-axis, and then she walked a total of 2 meters to her final position of 3.5 meters from the origin of this coordinate system. So her displacement would be her final position, 3.5 meters, minus her initial position, 1.5 meters. That gives her a total of 2 meters that she's traveled. That would be her displacement. And in this case, it also turns out that that displacement is the same as her total distance traveled. Displacement is actually a vector. So we're going to talk really briefly here about the difference between a vector and a scalar. We are going to work a lot with vectors this semester. They are going to be a big part of what we do here, and they can also be kind of hard, difficult concept to grasp, but we're going to work through them, especially in lab, okay? So a scalar is a quantity that does not have a direction, okay? It's just some number. So here's an example of something that's a scalar, something that is just 1 meter in length, something that is 100 or 10 kilometers in length, a speed of 35 kilometers per hour, a mass of 100 kilograms, a temperature of 20 degrees Celsius. Those are all scalars. They are a measure of something, but we don't have a direction, okay? And each quantity tells you something called a magnitude. The magnitude is essentially the size of that quantity. And again, it doesn't tell you which direction you're going. Okay? Magnitude is the size of a quantity. Scalars are often paired with directions to become vectors. So the important thing to remember about a vector is that it has both a magnitude and a direction. So a vector will tell you how big a quantity is, but it will also tell you in which direction that quantity is pointing, okay? And graphically, we represent vectors as arrows. So all of these lines that I've drawn here, these are vectors. They have a length, which is their magnitude, and they have a direction. So I could tell you, by a direction, I could tell you that this vector here is some angle of degrees with respect to the positive x-axis, and that would tell you your direction. The coordinate system, again, is really important when we're talking about displacement. And we will also encounter this in lab, but you'll have this in some of your homework problems too, eventually. Let's say that we have our coordinate system, our XY coordinate system. Here's our origin, okay? And let's consider the positive y-axis. We could also say that that's a direction pointing north, okay? The negative y-axis we could say is pointing south. The positive x-axis is to the east. The negative x-axis is to the west. So if I asked you to get in your car and drive 200 meters east, and then 100 meters north, I would be located somewhere up in this quadrant here. Especially if you're thinking about mapping something, it's convenient to consider motion upward or to the right as positive. So up or to the right as positive, and motion downward or to the left as negative, okay? So here is an example of, let's say we're driving our car and we want to talk more about displacement. So we are in our car and we start right here. And then we're going to move 3 kilometers to the left, okay? So our first change in position is going to be 3 kilometers to the left. We put a minus sign on here to tell us that we're moving to the left of where we said the origin of our coordinate system was, okay? Once we've moved 3 kilometers to the left, then we're going to stop and we're going to turn around, okay? And then we're going to move 2 kilometers along the x-axis toward the origin. So then we would move positive 2 kilometers because we're moving back toward the right, back toward the origin of our coordinate system, okay? So if we were to calculate our total displacement during this journey, we would see that we moved minus 3 kilometers to the left. We put a minus sign on it to represent leftward motion. And then we moved 2 kilometers to the right. We put a positive sign on it to represent our positive coordinate system. So then our total displacement is going to be minus 1 kilometers to the left. We still end up minus 1 kilometer from our initial starting point. So that's why we have that negative sign here. So remember that, again, that our displacement is a vector. So the displacement has a magnitude of 1 kilometer in the negative x direction, or 1 kilometer west of where we started from. Now we're going to practice those ideas, and you are going to find the displacement and total distance of 3 different examples. These 3 examples are examples A, B, and C that you see here. And I'm going to work through example D and show you how I would do this for example D, and then you're going to replicate it for parts A, B, and C, or for paths A, B, and C. So for each of these paths, I want you to tell me the distance, total distance that was traveled on this path, the magnitude of the displacement, and the displacement from start to finish. So the displacement, remember, has a direction, so we have to put a plus or minus on it. The magnitude doesn't have a direction, so we don't put any sign on the front of it, okay? So it's just a size. I'm going to work through example D here. So for example D, I start at 9 meters away from the origin. Then I move toward the origin to 3 meters away. And then I change my direction and I move back to 5 meters away from the origin. Okay, so what was my total distance traveled during this path? My total distance traveled was this path here from 9 meters to 3 meters. So this part here is 6 meters. And then I change direction and then I move from 3 meters to 5 meters. So that's an additional 2 meters. So my total distance from D around to back here again, my stopping point from start to stop, the total distance that I traveled was 8 meters. And then the displacement from start to finish. Remember, the displacement is your final position minus your initial position. So our final position here was at 5 meters. We are going to subtract that from our initial position, which was 9 meters. 5 minus 9 is negative 4, okay? So that means that my displacement is minus 4 meters. That minus sign means that I'm 4 meters away from my starting point when I end. Okay? That gives me a sense of direction. I'm 4 meters in the opposite direction from my initial starting point when I end. And so what's the magnitude of this displacement from start to finish? For the magnitude, it's just the size of that displacement. So I don't include that minus sign there. So for this, for part D, my total distance traveled was 8 meters. The magnitude of my displacement, the size, was 4 meters. And my total displacement, which has to take into account the direction, is minus 4 meters. And so I'm going to ask you to calculate all 3 of these quantities for paths A, B, and C.